So should I assume that everything is clear from the last talk? And have you gone through the assignments?
In the handout, I found it. I could not do it. Can you help me?
Yeah, surely. We in the next session we'll discuss many problems from the assignments. Like you'll also get another worksheet today after today's class. So you try those out and we'll discuss them later on. Yeah, some of them are tough. I agree, but we'll discuss most of them. Like whatever we can. The next session we'll discuss it.
Can we prove that am of mth power is greater than or equal to mth power of am?
Yeah, actually, we did it for the second power and said that let's assume for all powers, but we can actually prove it.
Is anyone saying anything? I can't hear it.
Yeah, actually, yes. So we are speaking. কোয়ানি তোটা কে ছিল রে? বুঝতে পারলাম না। আচ্ছা, তুই একবার চ্যাটে লিখে দেখ তো।
I was asking that how can we prove that am of mth power is greater than or equal to mth power of am?
Yeah, actually, we did it for the case 2, and I said that assume for the other cases. Well, if you want to prove it specifically for the other cases,
Some
I
sort
think
of
you can
induction.
do it. Yeah, exactly. Induction and AMGM should do it. Or you can use the weighted AMGM inequality over there to prove it. Okay, so it was pseudonym. Can you ask him to join audio? Yeah, okay, you can.
Yes, that I can hear.
Okay then. So okay, a possible proof using the weighted AMGM inequality would be as follows. Wait a second, I will share my screen. Okay. Yeah, right. Okay. So D2. A possible proof for the aim of mth power is lesser than equal to the greater than equal to the mth of power of am is the weighted AM's inequality as follows. Suppose the numbers are a1, am, all these greater than 0, then let w1 is equal to a1 to the power m minus 1 by a1 to the power m minus 1 plus a2 to the power m minus 1 plus dot dot. Our assumption over, I won't give m both ways. I'll keep this one n. Okay. So the assumption over here is m greater than 1. Then only our claim is true. Or plus an to the power m minus 1. And then w2 equal to the same thing with a2 to the power m minus 1 and the same denominator until go on till wn. So observe that with this definition, w1 plus w2 plus wn is greater than or is equal to 1.
Dada, this is the power mean equality.
Yeah, I'm using weighted AMGM to prove power mean.
Yes.
For m greater than 1, I'm proving that case. So these are the weights over there. And weights are as above. And observe that the sum is equal to 1. Then by weighted AMGM HM, we can only use weighted AM and HM over here. So we would have the following. Summation of WI AIs from I equal to 1 to n is greater than equal to summation of equal to, sorry, it would come below. So it's 1 by summation of I equal to 1 to n wi by ai. This is right. One second. Just check. Yeah. Yeah. Seems to be right. Yeah. Yeah. I'll just come back to it. I am not sure with this one. Yeah, I messed it up. Okay. Wait a second. We have to use this, but with some adjustments. I'll just look at the adjustments later. Let's continue from here. Left hand side is 1. No, it's not working. Wait, one second. Need better form quality over here. Okay. So the sum. Yeah, it's working. Sorry, I made a mistake considering the reciprocal. So over here, this sum, the sum given over here, left hand side is basically summation I equal to 1 to n. This thing over here is ai to the power m minus 1 times ai by, we get a1 to the power m minus 1 plus dot 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 plus a n to the power m minus 1. This is greater than or equal to 1 by summation I equal to 1 to n omega I is, again, we can simplify this stuff. So we get ai to the power m minus 2, and this summation goes on top. ai to the power m minus 1 I ranging from 1 to n. So you just substitute wi, the values which we chose above over here, and you will get this inequality. So what's this? Basically, this would imply summation I equal to 1 to n ai to the ai to the power m minus 1. So this becomes m ai power m times summation I equal to 1 to n ai power m minus 2 is greater than equal to summation I equal to 1 to n ai power m minus 1. Okay. Well, for the rational part, you can uh, straight away use induction after this. If you want to, you know the case for m equal to 2, and then follow it from here.
Will you scroll up a bit?
Yeah, sure.
Yes. Okay.
Okay. Well, we can do some inequalities over here. Otherwise, we want to do it directly, then we'll need another step of weighted AMGM over here, which says the following. it's again pretty obvious that a1 to the power wait a second. Yeah. M minus 1. Okay, you can follow from induction over here. I'll do something. I'll get back to this proof after I discuss Cauchy Schwartz maybe. That would be simpler. But yeah, you can follow this method to some extent. Well, the weights need to be a bit different for the next thing, next adjustment which I'm planning to do. The weights would be a bit different. But basically, it follows from all this inequality, and you can also change the weights to something else. Well, well, let's return to this at the end of the class. Okay. There is a proof using weighted AMGM. I think the inequality which I did, this one will work for rationals and induction, but there is a direct proof as well. I just need to assign the correct weights. Well, let's come back to this later. Okay. You can use induction over here, by the way. Like someone suggested, for the rational case, the thing which I asked you to prove, you can use induction over here, and this would be. But there is a better.
Dada,
Huh.
Dada, do we have to prove everything like whatever we use, like even AMGM or say
No, you don't need to
Menelaus
prove.
in the RMO?
No, you don't need to prove AMGM. AMGM, you can assume AMGM and Cauchy Schwartz. These two you can AMGM HM. By AMGM I mean QMS, AMGM, HM. That these four and Cauchy Schwartz. You can assume these two. And in fact, in Mo, in RMO, I don't know whether such questions came before. I don't remember exactly. But in INBO, you can also assume Jensen's inequality and stuff.
Oh,
okay. So it's you can assume inequality. You don't need to prove all this. Even in geometry, you can assume a lot of results, but not stuff like Pappus theorem and some Ptolemy's inequality and stuff. Avoid those.
Ptolemy you have to prove.
No, Ptolemy's theorem is okay. Ptolemy's inequality is something you can't assume because the proof is not that easy.
Achha.
Yeah. Okay. So let's return to the example which I was referring to in the previous class. Actually, I'll come back to this proof later, maybe. We had discussed the weighted AMG inequality. I hope you remember the statement. Let me state it once. Weighted mean inequality. Which states if A1, A2 an are greater than 0 and W1, W2 are also greater than 0, reals all, and sum of WI is equal to 1, then WIAI, this sum, is greater than or equal to the product. For sum, we use the sigma, the capital sigma, and for product, we use capital pi. AI to the power WI. The ranges are I equal to 1 to n always. I equal to 1 to n, don't forget to give this. And this is greater than or equal to our weighted harmonic mean. Yeah. Sigma equal to 1 to n WI by AI. Well, this is good. Now, I was wishing to give you an example at the end of the last class, but time did not permit it. So let's start with an example today. Okay. So example 1. It's given ABC are positive real numbers. A plus.
Can you wait
Hello?
1 second?
Yeah, sure.
We can write the thing.
Okay. So should I scroll up?
No, it's okay.
Okay.
হ্যাঁ, থ্যাংক ইউ দাদা, হয়ে
So
গেছে।
I'm resuming. Yeah. হয়ে গেছে তো, ঠিক আছে। Let me resume then. Well, a plus b plus c is equal to 3. It's given to us, and prove that for the first time till now, if you have realized, all the powers which we had in our examples and all, they were constant numbers, generally natural numbers, or if even if it's not natural, it's a constant number. Over here we will have the variables as the powers. Prove that a power b times b power c times c power a is less than equal to 1.
The handout of the worksheet is
Yeah. So how I think it's there in the worksheet, right? Or something similar to this is there in the worksheet. I think it was 3, the sum of 3 such quantities, as far as I remember. But okay, so as many of you have seen the worksheet, give your ideas over here. How do you want to proceed with this one? Anyone? Ideas?
we can prove that 1 greater than equal to ABC.
So how will that help us?
It was not helping.
Yeah.
Does the sum of the weights in weighted AMGM always have to be 1?
No, we can adjust that.
Right.
Well, that's pretty easy, right? Divide by
Sigma.
the sum of weight on both sides.
Yes, AB plus BC plus CA by A plus B plus C. We have to prove that is less than equal to 1. And then we can substitute A plus B plus C as 3. And then it's just directly AB plus BC plus CA is less than equal to 3 times A plus B plus C.
Okay, yeah, we'll do that. Correct. Good. So basically, the best thing over here is if we assign weights as such, W A, or the weight of A, is equal to it's B by A plus B plus C. W of B is equal to C by A plus B plus C, and W of C is equal to A by A plus B plus C. You can also write it as, which is obvious because A plus B plus C is given, as B by 3. W of B is equal to C by 3, and W of C is equal to A by 3. Okay. Should I scroll up because I went a bit fast? Or is it
Yes,
okay?
Bhaiya.
Okay, I'm
Once.
scrolling up. Yeah. I didn't realize.
Done. Thank you.
Okay then. Yeah. Welcome. So using this weights, by weighted EMGM, you will have WA of A plus WB of B plus WC of C. This is greater than or equal to W. Wait a second. A to the power WA, B to the power WB, C to the power WC. It's easy to check that the sum of weights is 1, right? Because from the first representation, it's obvious. And even from the second one. Now, what's WA of A? What's WA of A? AB
B by 3.
AB by 3, right?
To the power.
AB by 3, right? And what's WB of B? BC by 3. WC of C is CA by 3. This is greater than equal to A to B, B to the power C, C to the power A, by whole to the power 1 by 3. That's what we have. But note again, I think we have discussed this inequality before. BC plus CA is less than equal to A square plus B square plus C square. Right? So this would imply 3 times AB plus BC plus CA is less than equal to a plus b plus c whole square. But what's this? By our definition, it's 9 because a plus b plus c is 3. Hence, ab plus bc plus ca by 3 is lesser than equal to 1. So this thing over here is less than equal to 1 from this step. You guys write it properly. I'm just giving you the ideas. Hence, this proves our inequality. So this, along with this bracketed thing, would give us a to the power b, b to the power c, c to the power a. Taking a third power preserves the inequality because since this is a positive quantity over here, and even third powers have this property that it's not necessary that it's positive, but because it's a positive quantity over here, you can take a third power and still preserve the inequality. So you get this. Okay, guys, note it and let me know. And then you can try the other inequality which is given in the assignment. Over there is a sum of 3 such powers. It's pretty similar, but it's also a good problem to practice.
Can you re-explain why we are multiplying 3 over there in the second step?
Oh, we are not multiplying 3, sorry.
Adding.
I should have written it better. We are adding 2ab plus bc plus ca. We are adding 2 times this quantity because that's basically the expansion for this square. You're from your basic algebraic identities which you have done. You're not multiplying 3. This 3 is basically, you can write it as 1 plus 2 times ab plus bc plus ca. This is 1 plus 2 times ab plus bc plus ca. 1 is for this one and 2 is just straight away addition. And because it's a constant addition, it's constant with respect to the inequality. We are adding the same thing on both sides, so the inequality doesn't change.
Okay.
Okay, so let me know when I should continue. When you have noted the proof and you've understood it.
Continue.
Okay then. So you'll have some more examples of weighted engine, as I said in your assignment, and as well as power mean. You actually one on a suggestion, you should avoid using weighted AMGM and power mean directly, like in the general form, power mean or weighted AMGM directly in the examination if you can. But when you have such things like power of variables, like rather a variable raised to the power variable or something like that, sometimes weighted AMGM is your only option to make it easy. You can also do stuff like rearrangement, but then it would require logarithm and stuff. And let's not deal with it right now. I'll come to rearrangement inequality today if time permits later on. But first, I'll discuss another very important inequality for Olympiad as well as learning mathematics purpose. So, I'm continuing over here. Basically, let's observe something. For two variables, I want you to do this example directly. I'll call it example 2. This is a simple AMGM and completing square exercise. Prove that A square plus B square times C square plus D square is greater than or equal to AC plus BD whole square for all reals. Over here, negative, positive, nothing's given. For all reals, A, B, C, D. And find cases of equality. Find cases of equality. By the way, I didn't mention it yesterday, the day before yesterday most probably. This symbol means for all. Or I'll just remove the symbol for now. It's not that important. For reals, A, B, C, D. So how do you propose we should move forward? Just knowing,
And then
yeah,
it came with MGM, it got proved.
yes,
And did the bracket, and by then after
yeah, you can do that. Well, basically, if you open the brackets, the left hand side is A square C square plus A square D square plus B square C square plus B square D square. This is greater than or we need to prove equivalently. This thing is greater than or equal to the given inequality is true if and only if the following inequality is true. A, B, C, D, and you can cancel these terms off. So this first given inequality is true if and only if this inequality, which I wrote down over here, is true, which is true if and only if A square D square plus B square C square minus 2 AD BC is greater than or equal to 0, which is true if and only if AD minus BC whole square is greater than or equal to 0, which is true. And because all of these are if and only if statements, like you can add, every step can be inverted, our given
MGM also,
inequality is true. Yeah, you can do AMGM on this step as well. You can also do AMGM on this step. Yeah, it's the same. Square inequality and AMGM for two variables is the same at the end of it. So yeah, you can do AMGM in this step directly, and that's that. Okay, then. But can we generalize this to more variables? That's a question which we want to answer. So what I mean by generalization, once you've noted this, I'll move on. Okay, so should I continue?
Zyada.
Okay, and for that thing, I just remembered a part of it. And for my notes, I just noted that the first question which we were trying to answer about the AMGM, the AM of mth powers is greater than equal to mth power of AMs. Yeah, the method I stated with the weighted means it's good for the part of rational powers basically, but we can't use that method directly to prove it for real powers most probably. Because what I was intending to say is we have to make another assumption, which is Jensen's inequality. So it's no point doing it using this method. Well, you assume it for now.
Go like this backward, or we have to start from AD minus BC whole square?
In the examination, You should always, as I said earlier, you should always start from this step. I'm just giving you the steps and hints. These are not the proper proofs. When you write it, you have to write, it's given ADVC is reals, and then you'll say we show that this inequality is equivalent to proving AD minus BC whole square is greater than or equal to 0, which is truly true by the square inequality and order properties of reals. Then you prove the equivalence. This is because this you keep on opening, and then show that these two inequalities are equivalent using these steps. And then you can skip this if and only if symbols. You can just write one-way implications if you want to, because it's good enough. But it's always good if you have an invertible process going on over there. Even in science, you have seen it, and even in mathematics. If you can invert the whole thing, the best functions are the bijective functions. The best matrices are the matrices which can be inverted. If you have done matrices, I'm not sure about it. I don't think not, but still. So it's good if you can invert the whole process step by step. So if and only if is a very important thing. Okay, then let me move on to the generalization which I was referring to. Cauchy, Schwartz inequality are generally written as CS inequality.
Dada, did we prove the previous example?
Which one?
That a square plus b square, that one.
I actually discussed the proof over here. This is the proof actually. When you open this side, the left hand side, you get this. When you open the right hand, when you open the right hand side, you get this. So then cancellation of terms, like treating them as constants and equalities, you get a square. And that's basically the proof. Well, you need to write it a bit properly over there. As I said, you first need to write given ABCD are reals, then showing this inequality is equivalent to showing that this inequality is true, and then you show how these two inequalities are equivalent using these steps. And one thing, because it's an if and only if over here, we can avoid going backwards always. Once you write that this inequality is equivalent to that inequality, you can just write if and only if, and that would do, because as I said, any if and only if equivalence is invertible. You can go reverse direction as well. That's good.
Okay, Dada, thank you.
Okay then. So let's go to Cauchy-Schwarz inequality, CS inequality. This is the this inequality has many statements and many forms. I'll state one of them. A1. Okay, one thing I forgot. When I asked you to find the case of equality, so when does equality hold in this inequality? Just tell it from this square.
AD equal to BC?
Exactly. So inequality holds if and only if AD equal to BC. So we'll try to use this, but in a more generic setup, I might say, in the next general inequality. So we assume A1, AN are positive, are real numbers.
Can you please
Yeah?
repeat the spelling of that inequality? It's very hazy.
Yeah. Okay, I'll just repeat it. It's Cauchy, Cauchy, Augusta Louis Cauchy, and it's Schwartz, Schwarz. Many write it as Schwartz, but it doesn't matter that much. Both of them are acceptable. It's sometimes just known as Schwarz inequality, by the way. After Schwartz. So let's continue. We say A1, AN belong to reals, and P1 Pn belongs to the real set minus 0 set. Okay, why I'm making this assumption, it would be obvious in a few seconds, but you can avoid this assumption with another form.
It will become 0.
Yeah, because like some of them would become 0 and some trivialization might occur over there. So that's why I'm avoiding it. And you can actually avoid this, and I'll leave it to you as an exercise to generalize this even to the case when these two can be 0. A1s can be 0 over here, but B1s I'm avoiding them to be 0. There is a reason. Okay, so
But isn't the inequality symmetric over A and B? Like you
yeah,
are,
it's actually symmetric over A and B. It's perfectly
then
symmetric over A and B.
how can we do different conditions then?
Sometimes for the equality case it's good. Okay, then if you want the whole general statement, I can give that. Or you can do like as someone said, like we can assume that both of them are non-zero, and that would bring symmetry. But actually, okay, well, I'll give the generalization later. Let's assume both of them non-zero for now. Okay.
Right, you're considering positive reals, right?
No, it's not the positive reals. It can be any real number over here.
Both A1 and B, both.
Yeah, any real number. In fact, they can also be 0, but I'll discuss the non-zero case right now. As someone said rightly, that in 0 case, some trivialization occurs. Like some squares are not required and some multiplication becomes 0 and stuff. Okay, so then the statement of the inequality is as follows. A1 square plus an square, this sum, times b1 square plus dot 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 plus bn square is greater than or equal to a1 b1 plus an bn whole square. Basically, you see, we did the n equal to 2 case just in the previous step. We discussed the n equal to 2 case, because then a1 square plus a2 square times b1 square plus b2 square is greater than equal to a1 b1 plus a2 b2 whole square. With equality, if and only if a1 by b1 is equal to a2 by b2 is equal to dot 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 an by b. Well, as I said, we can generalize that to real numbers, but then you can't do division, and this equality case becomes a bit messy, to be honest. So that's why I avoided using equality. Using real 0. These can't be 0. I'm avoiding the 0 case. That's all. So, and actually for the symmetry thing, you might say that then why is it symmetrical, as you just said right now, which is right. Then you need to also see that this is true for non-zero real if and only if b1 by a1 is equal to b2 by a2 by invertendo is equal to dot dot dot. It's equal to bn by n. That's why either one of them must be all non-zeros for us to write in this form, the equality in this form. So let's discuss the proof of this inequality. Okay, I'm not sure whether you have you done the discriminant of quadratics?
Done.
Yeah,
Yes, Dada.
and that it's greater than 0 and stuff.
Yes,
If it has real roots, you have done it, right?
As for this, from Math
yes.
Club.
The maths club হয়েছিল কি ওটা?
Sahil Dada took our classes.
Yes,
Oh,
Sahil Dada
okay,
taught that.
then we can discuss.
Can we take any permutation over A and B?
Yeah, you can take any permutation. That's your liberty, and actually you can write it like that. But does it matter? I'm writing in general b1 b2 bn. Then just choose another b1 b2 n, which is the permutation, and that works.
Yes.
That's why you don't need to write that much and complicate the inequality actually. But you can take many things. You can take permutations and stuff, whatever you want. So okay, then I'll write this proof using discriminants. This is a beautiful proof. We consider the quadratic equation fx which is defined as a1 x minus b1 whole square plus dot 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 plus an x minus bn whole square. Okay, so what is this? If you open the squares and add it up, this is basically sigma ai. I'm not writing I equal to 1 to n. You guys assume it. Sigma ai square x square minus 2 sigma ai bi times x plus sigma bi whole square. This whole square is inside, this whole square is inside. So fx, our function fx is the following, and it's a quadratic equation. Now, what's interesting about this quadratic equation? Anyone? So, any interesting property which you note about this quadratic equation?
It is 0.
Dada, only 1 minute is left.
Okay, then you guys try to figure out how we can use this quadratic for the proof. We'll continue after the next session. Okay, Kwani disconnect করে দে, আবার join করে নেবো সকলে।
Maybe we can set x as 1.
Dada, it is of the form aix minus bi square like that.
Okay, you guys note it because I think the session's going to be over. So you
কটায়
guys
স্টার্ট
rejoin.
করব
কটা বাজে রে?
সঙ্গে সঙ্গে
Okay, so should I start?
someone found a solution, so you can check the
Yeah.
solution.
Yep. Surely. And share your solution. Wait a second, I'll just share my screen so that I can write down whatever you see. Okay. So tell me.
Can I tell my solution?
Yeah, surely. Tell me your solution.
Okay, so the quadratic function you assumed equation,
Yeah,
it is a sum of some real squares.
exactly.
So it is greater than or equal to 0.
Okay.
Okay, so now we know that that its discriminant is always greater than equal to 0, because if the discriminant is lesser than 0, then it will cross the x-axis, and for some value of f of x it will be less than 0. So it has to be greater than or
I
equal to
think
0. And
you said the opposite.
oh, sorry. If d is
Yeah.
greater than equal to 0, we will have greater than 0. We will have real roots. So the parabola will at least once cross the x-axis, and we will have at least one value of f of x, for which it is f(x), for which f of x is less than 0. So d is always lesser than or equal to 0, and thus we have proved the solution.
Exactly. Wonderful. So that's what we'll do. So I hope you got what he said. Let me write it down. Okay, so we had this fx over here. I think it's visible now. Fx is equal to a1x minus b1 whole square plus so on. Note that fx is always greater than or equal to 0 for all x belonging to R. So for all real x, fx greater than or equal to 0. So what does this tell about the discriminant of f? So discriminant of f, as you might know, is less than or equal
How
to
is it
0.
always
Other
greater than equal to 0?
is the sum of real squares.
And the minus 2 sigma aibi times x, that part?
I think you missed the first step. The first representation
Okay,
says that it's the
okay,
sum of
got it.
squares. Yeah.
Yes.
Okay then. So you have this. Now using df less than equal to 0. So suppose df was greater than 0. From your quadratic equation in class, this would imply f has two distinct real zeros. So there is an element, because our leading coefficient is a positive quantity over here. This would imply that there is some real y such that fy is lesser than 0. But that's a contradiction, right? It contradicts this fact. So this thing, discriminant f greater than 0, that's not possible. So we have discriminant of f less than equal to 0 for sure. So what is the discriminant of f over here? Let's look at the quadratic once again in the second form. So what's the discriminant of f?
Yeah.
It's b square minus 4ac.
Greater than 0.
Okay then. So we have 2 times sigma ai bi whole square. This is our b square, or the coefficient of x whole square, minus 4 times coefficient of a, which is sigma ai square, times coefficient of c. Yeah, coefficient. Sorry, I meant coefficient of x square, which is sigma ai square, and the constant term, which is sigma bi square. This is the discriminant. Df is equal to this, but this is equal to 4 times. If I put a bracket over here, sigma ai bi whole square minus sigma ai square sigma bi square. This is b, by the way. Okay, wait. Bi whole square. Very good. And what's df? I know df is less than or equal to 0.
So from df less than equal to 0 and this, if I call this 1, if I call this 2, from 1 and 2, we have sigma ai bi whole square is less than equal to sigma ai square times sigma pi square. So that's what we wanted to prove. And now for equality case. Equality will hold if and only if there is an equality in 2. So let's write it down. For equality, df equal to 0. So what would df equal to 0 imply? There is a real solution of our f. This f over here has a real solution and a unique real solution for that case. So there is a C unique such that fc equal to 0. But fc equal to 0 would imply one thing. From our first form of fx, I hope you remember the first form of fx would say
that aix minus bi is equal to 0.
this whole square is equal to 0 for all I belonging to a set 1 to n. That's the general square inequality which we discussed in the last class. So this would imply, because ai not equal to 0, this would imply c is equal to pi by ai. In fact, all this can be considered to be if and only if for all I. So what does this tell? C equal to bii for all I. This is if and only if a1 b1 is equal to a2 b2 is equal to, sorry, a1 by b1 is equal to a2 by b2 is equal to an by bn, which is if and only if b1 by a1 is
Can you scroll
equal
up
to
a little?
b2 by, yeah, surely. I'll just write this down and scroll up. One second. Is it okay? Or a bit more?
Thank you.
Okay, then. So is it clear what I just said? Why this is the only equality case? Now you obviously realize there is some problem if some of these AIs are 0 or something like that happens. And if the AI is a 0 and BI is not equal to 0, then this is a strictly greater than 0 square. And that's not good for us. And many more problems occur using this method. And you realize why I wanted the AIs or BIs to be 0 to make it simpler for us. To be non-zero, I meant. That makes the case pretty much simple for us. So I'd recommend you try to generalize this inequality and find the equality case when some of them are permitted to be 0. But I don't think you'll encounter much of them because generally the Cauchy-Schwartz which is required for inequality arises from standard inequality stuff where it is given positive, let alone non-zero, it's given positive, or geometry, again positive. But still, I'd recommend you go through it because you never know what might come. Okay, then. So is the proof clear, everyone? Hello?
Yes.
Yeah. So the proof is clear?
Yes, Bhaiya.
Okay. So if you have any doubts in the proof or any other previous problem or discussion, feel free to stop me at any moment and share that. Otherwise, I won't sort of get to know that you are facing any problem. I won't be able to help you, even if I could. Okay, then, assuming that you have no more problems or doubts over here with the proof,
Dada,
let's. What?
I didn't understand that equality case.
Okay.
And a DF equals to 0.
So okay, let's look at it. Suppose df equal to 0, then this would become equality. This part is clear, right?
Yes.
Then what does discriminant of a quadratic equal to 0 imply? It has a double root, or it has a unique solution. That is, C is unique. There is a unique C such that FC equal to 0. Or there is a root, let alone unique and all stuff. There is a root.
Yes.
But what will a root imply? With our first representation of f, which is that f is the sum a1x minus b1 whole square plus a2x minus b2 whole square and so on. That would imply ai ci minus bi whole square. This term is equal to 0 for all I by belonging to this set. That means a1 c minus b1 whole square equal to 0, a2 c minus b2 whole square equal to 0 and so on.
Yes, Dada.
And what does this tell you? That if x squared equal to 0, that's if and only if x equal to 0. So that means ai ci minus bi is equal to 0 for each I. So this is if and only if ai ci minus bi is equal to 0 for all I, which is if and only if c is equal to bi by ai for all I. But if c is a constant unique root, I know it over here, and it's equal to some BIAI for each I. That means that all of these quantities BIAIs over here are equal. But by invertendo, that would imply that A1 by B1 is equal to A2 by B2 and so on, later AN by BN. Hence that.
Oh, yes, yes, got it.
Yeah. Okay then. So now I hope that there are no more doubts or questions over here. So I'd like to move to an example. A simple one first, just to see the power. As someone said, a permutation. So I'll try to give an example where it will involve a permutation, and a pretty strong one. So I'll write example 3 first. A, B, C greater than 0. See, in our first example itself, we have a greater assumption. We don't need the 0 case. We don't need negative cases as well. We are just considering positive reals. Then I need to prove using Cauchy-Schwartz. You already know this inequality. I'll prove this using Cauchy-Schwartz. Actually, you can also generalize this over here, but let's just do it for positive reals. Saves us a lot of trouble. So how do you suggest what should be our A1, B1? What should be N? What
Plus
should be
to b square plus c square into c square plus a square greater than equal to a square plus b square plus c square?
Yeah, I didn't get what you said. Can you just repeat?
plus b square into b square plus c square into c square plus a square greater than equal to 2 into a square plus b square plus c square?
You're saying a square plus b square times b square plus c square times c square plus a square. You're saying this thing. How are you planning to use this? And we have two products over there. We have three products here. So how are you planning to use it? If you could just tell us your idea.
What do we have to put again?
We have to prove this thing. This inequality over here. Using Cauchy-Schwartz. Okay, I'll remove this because I don't think this would lead us to any useful solution. Maybe it can, but not using Cauchy-Schwartz. Okay, so let me give you a hint. I said permutation. So think about permutations. What about the following? Using Cauchy-Schwartz, what is this greater than or equal to?
Can I share my proof?
Yeah, surely.
Okay, so let us take A1 equals to A, B1,
Yeah.
A2 equals to B, and A3 equals to C.
Okay.
And then B1, B2, and B3 equals to 1.
Very good. Yeah, and that will work. Yeah.
So we
this
get
one will work.
3 times A square
Yeah,
plus B
this will
square
work.
plus C square.
Yeah. What he
Plus CA
said is
whole
correct.
square.
We can also do this. We can also do using this one. So we'll see both of them. I'll call it proof 1, and I'll also write proof 2 using Cauchy-Schwartz, the idea which he gave, which is correct. So what is this greater than or equal to using Cauchy-Schwartz?
C plus CA whole square.
AB plus BC plus CA whole square. So this implies A square plus B square plus C square whole square is greater than or equal to, by Cauchy-Schwartz, this holds AB plus BC plus CA whole square. But both of these are positive quantities. So for positive quantities, x square plus y, x square greater than or equal to y square, if and only if x greater than or equal to y. So we can take the root and we get a square plus b square plus c square greater than or equal to ab plus bc plus ca. Now, what if we had general reals? Then you have to put a modulus. Over here, it's the square, so modulus is not required. You'll get a modulus, and this is greater than or equal to ab plus bc plus ca. That's for the general case. Well, then let's do something. Let's remove this greater than 0 from here. ABC just belongs to reals. That's what's given. And that completes a proof. And what about his proof? Let's state that one. He said, consider this. I think I got what you said correct. Not sure though. A square plus B square plus C square times 1 plus 1 plus 1. This is greater than or equal to A plus B plus C whole square. So then using some basic algebra, this is equal to A square plus B square plus C square plus twice AB plus BC plus CA. So use algebra and order properties to get A square plus B square plus C square. greater than equal to AB plus BC plus CA. Okay then. Now let's look at how the equality condition works using Cauchy-Schwartz. So in both cases, we'll look at the equality condition. Okay. So should I move on to the next page?
Actually, I had some problem understanding this. Can you explain again?
Yeah. Get
I had some problem understanding this. How exactly does Cauchy Schwartz apply?
Can you show the previous page once? I got disconnected, so I could not see it.
Okay. Then. I'm just going to the previous page. One second. This one. Wait a second. I'll go to the equality and start.
Yeah, thanks.
Okay. So for the Cauchy-Schwartz, someone asked that he has problem understanding the Cauchy-Schwartz inequality. Well, it says that give us a non-negative.
How
Sorry,
does
rather.
it apply in the last question? How does it apply in the last question?
Okay, then I'll come to it. Let her copy it. Then I'll come to it.
Yeah, thanks.
Okay. So, have you noted the other parts, like this thing, equality case, and so on?
Equality
Yeah.
resulting in A equal to B equal to C, right?
Yeah, equality will occur over there. A equal to B equal to C. That's known. We already know it. But how can we show that using Cauchy-Schwartz? That's important.
Square by C square equal to B square by B square equal to C square by A square, something like that.
Okay, we can do that. Okay, we'll come to it. Let her copy. Have you copied this part? Have you noted this part?
That A1 by B1 we can use with various permutation, will get A equal to B equal to C.
Exactly. That's what we'll do. But yeah, that's what we'll do.
First one I
But
got A
some,
equal to B, then I took another order, I got A equal to B, then it come A equal to B equal to C.
yeah, that's what will help. But how exactly are you getting A equal to B? That's important. Because I've generalized it to any real numbers. Now, if it were non-zero, then we can use this division and process. That's why I wanted to do it with non-zero first. And but we can generalize this inequality, and it's well known that we can generalize it. So then, what should we do? That's the question. Okay, then let's just skip the general case. Should we? Maybe you guys think of the general version of Cauchy-Schwartz first. That would be the exercise of today. An extra exercise for you. You think about it, and then next day we will write the equality using general Cauchy-Schwartz.
Dada,
Today,
can you just write that prove the Cauchy-Schwartz general case, so that
okay,
like those who will be studying from the PDF they can also do.
okay, I'll write it after the example. Okay, Konit.
Okay.
সেটা আর বলতে হবে না। Okay. So wait a second. I'll just go over here. Have you noted the proof? Whoever asked that she got disconnected, have you noted it? or should I wait? On it?
Yeah. Snehinh Dada, please unmute yourself.
Wait a second. Am I on mute?
No, we can hear you now.
No. Okay. Well. So, is this whoever asked that she did not note this part? Should I continue? Would you note the proof later on and then ask your questions on the next day or something? Because you can just note the inequality for now and get the intuition.
We have
we can
also
look at
given same exercise in one of the handouts, also with hints. So you can try from there also if you could not note down.
Okay, then so let's move to the example because you have a limited time over here, and I'll help you with your doubt if, on the next day or later on whenever you want to. So okay, so let's not wait. Sorry, let's not do it for the whole real number case as we were doing. Let's do it for ABC greater than 0 because for equality case that simplifies our job, and then using Cauchy Schwartz this step is not required. Okay, so let's look at the equality case now. For the first thing, our first brackets were a square plus b square plus c square. Our second bracket was b square plus c square plus a square. So for equality, the ratios must be all equal. So for equality,
by c
we
equal to
must
1 equal to c by a.
a by b is equal to b by c equal to c by a. So you can do many operations over here and stuff to get the answer. But I think you have seen something which is like multiplying equalities for if the ratios are non-zero, then how even if they are zero, how we can use root and operations to get another quantity which is equal to these cases. So can you show that this is equal to cube root of ABC by cube root of BCA just by using this ratio properties? Assign this to be lambda, then this is also lambda, this is also lambda. Show that this is also lambda. Just using property of surds and stuff.
We can't use AMGM here.
Why AMGM? It's an equality, it's not a sum. We just want to show that these three quantities, if equal, is also equal to this quantity, and it's equal to 1. Or you can simply, if you don't, if you don't want to do such stuff, and you might think that this is not necessary, then you can do the following, and this is easier. You take this is equal to lambda, then that would imply lambda cube is equal to a by b times b by c times c by a by definition, which is equal to 1. But lambda is a real number, so this would imply lambda equal to 1. Okay, and for the second one, it's easier. The equality case. It's simply a by 1 is equal to b by 1 equal to c by 1, and that's what's needed. Okay. Have you guys noted this part? I'll move on to another example, a bit different from the one we have already discussed. So should I?
Yes, Dada.
Okay. So example 4, right? How about this? Yeah, this one seems to be good. You'll see a generalization of this inequality with the one I'm about to state in your assignment as well, which you need to work out the worksheet, how you can generalize it. But let's do it. Well, once again, a square by b plus c square by d is greater than or equal to a plus c whole square by b plus d, where
It's
a, b, c, d are greater than 0.
Can you just move your page a bit above?
Yeah, surely.
Let's have a little below.
A little below.
Yeah, perfect.
Okay. So how do you propose we go for this one? You can again do square inequality and stuff. That's possible. But try to do it using Cauchy-Schwartz. Rather, I should ask my question as what should be x1 if I write it as this? Sorry, I should write y1 or x1 plus x2 whole square, y1 square plus y2 square is greater than or equal to x1 y1 plus x2 y2 by Cauchy-Schwartz whole square. So what should be x1, x2, y1 and y2 for us to have this inequality? So any ideas?
Can we take b plus d to that side and multiply?
Yeah, so you can do that.
Because
and then
b
we
will
can
cancel
simplify.
out, then we get b square. Yes.
Yeah, we can simplify using that, but I don't want to use it. I want to do directly using Cauchy-Schwartz. Then after you do that, you can use AMGL. And this is basically a very simple form equivalent to AMGL. But I don't want to use it. I want to use Cauchy-Schwartz directly. That's the beauty of Cauchy-Schwartz. You need to do it without. Sometimes you can do some inequalities which can be done with simplification without doing any simplification, just using Cauchy-Schwartz directly. So that's what I want over here. So you need to give me an idea of how I can use Cauchy-Schwarz directly over here in this set. Okay, then let's assume that you guys have thought. I'm sure you have some ideas, but I'll move and I'll give you a hint. Set x1 is equal to root b. Because b greater than 0, we can do this. And set x2 is equal to root d. And now what's y1? Idea?
A square and c square.
No, a bit more. A square by b.
Y1 square is a square and c square. Oh.
No. I want the
That
other. It's b square. Sorry, it's c over here. It's c by root d whole square. Then by Cauchy-Schwarz, take a product, and over here this becomes a, and this becomes c whole square. So what's this? This is if and only if this is simple Cauchy-Schwarz, right? What I did. But what's the left hand side? It's b plus d times a square by b plus c square by d. That's greater than equal to plus c whole square. And that's what we need to prove actually. The given inequality is the same as this one. These two are same. So see how proofs become pretty simple using Cauchy-Schwarz directly. Now that we have Cauchy-Schwarz, I think actually what I meant over there that you can use AMGM and stuff to prove power mean. Now you can try proving power mean for rationals. It would be easier because direct AMGM is a bit hard over there. So now try it out. But this is the proof which I was talking about, and this inequality is a bit special. It's known as Engin's inequality. You know the book by Arthur Engel most probably, or T2's inequality. You have a general form in the worksheet 3. Try to prove it using this and some induction, and you can use this one as well sometimes in the examination. But you see the proof is pretty short, and Cauchy-Schwarz is like given. So you can always prove this as a lemma and then use it.
Exam, we have to prove
and that's
this.
better. Yeah, it's better if you prove it. Okay. You can also use AMGM, by the way. Try the AMGM proof for this one. It's not hard. Okay, then. If you have noted, and also think about the equality case, it's not hard again. The equality case would be when A by B is equal to C by D. Because when you divide this by this, you get A by B, and when you divide this by this, you get C by D. So, let's look at one more example before I stop discussing Cauchy-Schwarz. I'll also give another alternate proof of Cauchy-Schwarz after this example, which is actually very helpful sometimes, knowing that idea. But should I go to the next example? Okay, then. Since no response, I'm assuming I've written it down.
Move forward.
Yeah? Okay. So example 5, this one would be a bit different. You can use, at least in this class, you can use T2's inequality directly if you want to. But think of a simple Cauchy-Schwarz solution always, if you can. Okay. So the question over here is to prove this is from some Olympiad. Don't remember the name exactly, but ABC equal to 1. This is given to you that ABC are positive reals equal to 1. Then you have to prove
Are you writing something?
Yeah, I am.
It's not visible to me. I can just see a blank board. Or it's only happening to me.
Is it visible to the others?
Till where have you written? I can see till ABC greater than 0.
Yes,
And then the proof that is not visible?
No. Now it is visible.
not.
Okay.
Or maybe some problem with my network. No problem.
Okay. And then we need to prove that 1 by b times a plus b plus 1 by c times b plus c plus 1 by a times c plus a. This quantity is greater than or equal to 3 by 2. I think it's not in the worksheet, but still, if it's there, it's good. Let's solve a worksheet problem for once. So, any ideas how we should proceed? The preferred method, as always, is just Cauchy-Schwartz. But give me your ideas. I want to hear. What do you want to say? Okay, so another equivalent form, one thing, another equivalent form, sometimes x square might be a bit confusing. And if this ABC greater than 0 is given, or in general, if positive quantities are given, then you can also write Cauchy-Schwartz as the following. x1 plus, if all these are positive, then you can write x1 plus xn, y1 plus yn is greater than or equal to root x1 y1. If all, as I said, all must be positive. x1 x1 to xn, y1 to yn, everything must be positive. Then you can also write this thing, yn xn or xn yn, whatever. This is also Cauchy-Schwartz. It's the same thing. So, any ideas you'd like to share over here? It could be anything, whatever you think might be a probable approach or might lead us to somewhere.
Replace 1 by b as AC. And
Can we
similarly,
somehow use
Okay, I get you say. You are saying that replacing 1 by b by AC, this inequality becomes AC by a plus b plus BA by b plus C plus CB by C plus A. Well, that's good. It's greater than or equal to 3 by 2. Yeah, that's good, but this won't be enough. Okay, so let me proceed a bit. I won't be using this most probably directly. So I'll make a substitution, which is sometimes helpful. Since it's given ABC is equal to 1, I don't want this additional information always. I don't want to run it behind my mind, at the back of my mind. So Rather, I'll use this. Because ABC equal to 1, there are positive reals x, y, z such that a equal to x by y, b equal to y by z, and c equal to z by x. So we have actually used the information that ABC equal to 1 over here. Is this substitution clear? Like why I'm doing this? So
Yeah.
we don't need any restriction on xy other than they are positive reals. So this would imply in our inequality, what will we have over here then? 1 by b is y by z. And what's over here? A plus b, right? So it's x by y plus y by z. Okay then. Okay, so let's continue over there. I think it got disconnected. Okay, is it visible, everyone? Okay, so what was the inequality once again? Okay. So here it is. Z by x times y by z plus z by x plus 1 by x by y z by x plus x by y. We need to prove that this is greater than or equal to 3 by 2. So we have actually not, we did not lose any information, but still we got a better form over here. Why better? Like we don't have any restriction. Once we have utilized the information, we don't have any restriction on XYZ. Earlier we had a restriction of ABC, which to implement and to remember might be a problem sometimes. Okay, so let's simplify this and rewrite. This is z square y. Oh, the y would get cancelled. That's good. So xz plus y square plus x square by yz, or what's it? Once yx plus z square y square y square by yz plus x square. This is greater than equal to 3 by 2. So this is the inequality which we need to prove. So
it will be z square, right? The first.
Which one?
Yeah, you that is z square by xz plus y square in the first term.
Yeah.
What you have? Acha, that is square.
So
Okay,
I've
I
written.
didn't.
Oh,
Okay,
acha.
okay.
You thought that's a single z. Okay, sorry. Yeah, it's z whole square. Is it better now, or it's worse? It's yeah. That's just right. The two proof is equivalent to proving this is equivalent to proving this for all x, y, z. Okay. So I'll just scroll up a bit so that the last line is visible. But from our knowledge of whatever knowledge we have of Cauchy Schwartz, we know this thing for now. We know but in Olympiad you don't write we know, you have to write that we can prove or something like that. That's better. You don't want to lose marks or those stuff. Okay, we know this. Now we would like to utilize it over here. So how should we utilize it? Well, you would have the following. Okay, so can we use this directly? That's my question. Oh yeah, I forgot to pose or so can we use this? Is this gonna work? Plus x square by yx plus z square plus y square will this work somehow? That's my question using Cauchy Schwartz.
Suppose from that, if you got that adding x, y, y, z, zx whole side, we got it is always greater than 2yz plus 2xz plus 2xy plus 2yz plus 2zx. By symmetry, if we said 2zx xz by 2zx, then y square. Similarly, we'll get 3 by 2, 1 by 2 plus 1 by 2 plus 1 by 2.
You're suggesting some kind of assumptions on x, y, z. Is this symmetric? This inequality? You just said symmetric. Is our inequality symmetric?
Yeah, it's looking very much symmetric.
Looking symmetric. That won't do. This inequality is not symmetric. You replace y by x, you get a different inequality. This is cyclic. This inequality is cyclic. It's not symmetric. Like the inequality is the same thing if you again consider x, y, z to run over anything and then do other substitutions. But the definition of symmetricity is even if you replace two x and y or something like that, it's still the same. Over here, it's not the same. It would change. This inequality is not symmetric. You can't do that. Okay, so now back to my question. Can we use this inequality over here somehow and do Cauchy Schwartz? well, let's see whether we can use it or not. Now by Cauchy-Schwarz, this is greater than or equal to z by, this would get cancelled and we have to take a root, so it's z plus x plus y whole square. That's what Cauchy-Schwarz would give us. Let's call this whole quantity inside the bracket, or rather the this thing as t. Let's call this t. Okay, to make it simpler, let's call this t. Then this is if and only if t is greater than or equal to x plus y plus z by, this sum is nothing but x square plus y square plus z square plus, there's a whole square over here, plus xy plus yz plus zx. But is it of any use? Like, can you show that this is greater than or equal to 3 by 2 or anything like that? Then we can show t is greater than or equal to 3 by 2. But is this true, the inequality which I'm stating? Actually, I hope that you're trying it out, but if you try it out, you'll realize that this inequality is not true. Rather, the opposite inclusion is true. So we can't use over here this direct method.
Greater than xy plus yz.
Yeah, this opposite inclusion is true. So basically, we can't use this method directly. Like a direct Cauchy-Schwarz or something like that isn't working well with us. So now I've done some ideas from you guys, like how you would want us to proceed if you have a situation like this. Like you are getting a weird inequality once again. Okay then. As we have limited time, I'll continue with the proof. So what do we have? T is equal to this quantity, which we have set as z square by xz plus y square plus y square by, this would be an z square, right? No, this would be x square. So it's yz plus x square by xy plus z square. And we need to prove that t greater than equal to 3 by 2. So a very sort of obvious step over here to make it a bit simpler or better would be to make the RHS better. When you are having Cauchy-Schwarz or something, a 3 by 2 or something like that won't go well, right? The inequality, like for AMGM or division is good. In Cauchy-Schwarz, it's always multiplication or natural sum. There can be a half factor, surely.
Can
but
the
it's
RHS
better if you have
plus half?
Huh? I didn't get you.
Can
Repeat, please.
the ABC plus half? Oh, but we have eliminated. Sorry.
Yeah. So we don't have any ABC. We don't have any restriction on XYZ. That's what we wanted. You can try using ABC and other properties of ABC as well. And sometimes it does give good results. But over here, let's see a more generic approach. So instead, I'll prefer to prove the following. If I can show half plus z square, z plus y square, this thing, and the product taken. Wait a second, I'll just rewrite it. That has half as necessary. This is equivalent to our given inequality, right?
Yes.
It's the same thing. So we haven't sort of achieved anything great over here. But let's add it to everywhere. That would make it better. And over here, plus 6. So what do we get? It's 2z squared plus xz plus y squared. Okay, is this, just tell me honestly, is this example getting a bit too much for the first class on Cauchy Schwartz, you guys? If yes, then we'll discuss it tomorrow maybe, or tomorrow, day after tomorrow, whenever we have the class. You guys try it on your own? Will that be better? Because you have just learned Cauchy Schwartz. I just realized this might get a bit too much of hand. Will that be better for you guys? Hello?
Yeah, maybe yes, we can discuss this later.
Okay, then that would be better because I think from your voices it's a bit confused. Because let's discuss a simpler example then. Let's skip this example for now.
Keep track of.
Dada, how did you
Complete this example, I guess.
Many are saying let's discuss it on the next day. So it's better because it's a bit like too much for the first day. I agree. Like this example, I'll send you hints. Maybe you can go using many methods. I'll send you another method as well for this one.
You can just provide us some hints. We'll try till the next class and come up with our own perspective.
Okay, the best hint is using Cauchy Schwartz. That's like the best hint over here. So like using Cauchy Schwartz after adjusting this, because in Cauchy Schwartz a greater than equal to 3/2 is not that good for you. That's not something which you would want.
Yeah, you have shown till here. We'll try to move forward.
Yeah, you try using. You have to prove this inequality. Try to prove this maybe. That would be a good hint. And yeah, you can use some other inequality and stuff as well if you want to. I won't restrict you over there, but it's better if you restrict and you do Cauchy Schwartz itself and no other advanced stuff. But yeah, so I'll maybe the substitution over here and try it, and everything was a bit confusing. Maybe I'll post a solution or send a solution to Connect. You go through it, and then we'll discuss it in the next class. Maybe next class would be more of problem solving, so it would be easier for you. Okay then, because yeah, this is a bit advanced. I should have chosen a problem like that. Okay, let's look at another example, maybe a simpler one, a far simpler one. This is straight from the assignment, by the way. So, well, okay, doesn't matter. This is far more simple compared to this one. We have to just prove the following inequality. Root over 3a square plus ab. Again, given abc are greater than 0 plus root over 3b square plus bc plus root over 3c square plus ca is less than equal to twice a plus b plus. This is simpler. I think I have given it in the assignment, but it's okay. So try this one. I'll just pause for a minute for you guys to try. Then give me a solution. Whatever ideas you have, feel free to share.
Well, squaring just hold the inequality.
Squaring might not help. Yeah, might help. Okay, let's see what happens if we square. And then we will again get a root. So we can't do away with the roots, right? So is it any help squaring it? Why don't you use the second form of Cauchy-Schwartz, which I just said?
Can we use T2's inequality here?
Yeah, we can. Cauchy-Schwartz and T2 are equivalent, so we can. But try something easier, maybe. This is direct Cauchy-Schwartz. Just to visualize it is a bit difficult. Okay. As you said, by the way, whoever said it's right. You can square to make it and not expand to make it a bit visually simpler. Root 3b square plus bc plus root 3c square plus ca. We don't expand, we just write it as a square.
A common.
Yeah, exactly. That's what we need to observe. Times 4 a plus b plus c whole square. But what's this? Let's rewrite it. This is true. This inequality is true if and only if this is true. This is true if and only if 3a plus b times a plus root of 3b plus c times b plus root of 3c plus a times c whole square is less than equal to
b plus c whole square.
4a plus 4b plus 4c times a plus b plus c. But what's 4a plus 4b plus 4c? We can rewrite the left hand side over here. Sorry, right hand side over here as less than equal to 3a plus b vinculum over here plus 3b plus c vinculum over here plus 3c plus a times a plus b plus. And that's Cauchy-Schwartz. This is Cauchy-Schwartz. And that's what we need to prove. So this is basically a restatement of Cauchy-Schwartz inequality. That's it. With some weird values instead of x, y, z. So did you get this example? Was this easier? Just go to the example once and then let me know. Okay then. So should I assume that you've gone through it and understood it?
I could not.
As there are no doubt.
There's a bit of difficulty in applying Cauchy was in last step after the root 3a plus b to a after that step.
Okay, so basically, Cauchy-Schwarz in the second form, as I wrote, you can use this form of Cauchy-Schwarz as well. X3, if these are all positive, this is nothing but again Cauchy-Schwarz inequality, right? There is a whole square over here. Yeah. Set like instead of our square terms, we are using like this is nothing but x1 square, x2 square, x3 square, y1 square, y2 square, y3 square, and this is x1, x2, y2 whole, and these are whole square, and then you can remove the cert. So these two inequalities, one I wrote and are equivalent. So we are using this form of Cauchy-Schwarz. I just mentioned it above at the beginning of the previous example, most probably. Wait a second. Yeah, over here. We are using this form. So how? It's basically over here, x1 is 3a plus b, x2 is 3b plus c, x3 is 3c plus a, as given over here, and y1, y2, y3 is abc, and then it's this inequality, just written in the opposite direction. So is it better now? Like, did you get it?
Yes.
Okay then. Like, it's confident yes, right?
Provide another proof for Cauchy-Schwarz now.
Yeah, I'll state another proof of Cauchy-Schwarz now after this example. So now this example is over. So now let's come to the alternate proof of Cauchy-Schwarz. Alternate proof. This is a very useful proof. And here we will make a further assumption, as we'll see that this assumption isn't much required. We'll assume A1, AN greater than 0, B1, BN greater than 0. You can do away with this assumption as well, but I'll assume this for now. You guys think how you can generalize. This is better because I'll prove the second form of Cauchy-Schwarz, or the first form, it doesn't matter. Yeah. So we define a new quantity. Xi is defined as ai whole square by a1 whole square plus a2 whole square plus a
What is
n
that?
whole square. It's wait a second, I'll just rewrite it. It's ai whole square. Okay. So basically xi is a new quantity which is nothing but ai whole
Dada,
square. Huh?
do
Yes.
we need to prove that Cauchy-Schwarz in the exam?
No, we don't need to prove Cauchy-Schwarz. As I said, you can assume Cauchy-Schwarz and AMG and QMS. These two, if problem is better. Yeah. So xi are defined as such for all I. And similarly, yi is defined.
Yeah, your screen has rotated.
Yes, it has rotated.
So you have xi's and bi's over here. Observe the following two properties. Sum of xi's is equal to what is the? It's 1, and the same is for yi's, right? Isn't this obvious?
Yes, Bhaiya.
Okay. So now we consider the following sum of xi plus sum of yi. This is nothing but 2, or written in an alternative form, this is nothing but summation I equal to 1 to n xi plus yi by 2. You can take the yi's inside for each I and write it as this is equal to 1. Correct? We can do this, right? Whatever I wrote makes sense to all of you, right? But by
Yes.
AMGM, this left hand side is greater than or equal to, we have 1 is equal to the LHS above this thing. It's greater than equal to, this is the place where we use AMGM, summation I equal to 1 to n root over xi by n. This sum. But what is root over xi by over here?
A product.
Yeah, it's a product. What exactly is root over xi by I? From our definitions of xi by I, it's nothing but ai bi divided by the root of sum of ai whole square times the sum of bi whole square. Is this right? Just look at our definition of xi and yi, and this follows immediately. So I'm moving to the next step. So this implies 1, rather I'd write 1 is greater than or equal to. Now, because this factor is a constant for each I, we can, the sum of all, yeah, I'll use aj instead because there is a I above. So I'll write it as aj and bj. Sum of aj whole squares and sum of bj whole square. Just not to confuse you guys. And 1 is greater than or equal to sum of I equal to 1 to n ai bi whole divided by, because this is the same for each I. This is the sum of all of them. So it doesn't change with I. So we can take it out of the sum as a constant with respect to the index I. So it's root over sum of aj whole square times sum of bj whole square. And this is Cauchy-Schwartz for you.
J. Why are we considering J?
Oh, it's basically because to avoid there is an I above, right, in the sum, and this sum is taken before we sum over I. So that's why I'm doing like a different index. This is basically nothing. This is a sum from j equal to 1 to n. This is a constant over here. That's why I want to use. It's not dependent on I. The sum for each term I, this is not dependent on I. The denominator is independent of I.
Okay, then.
So that's why I used a different index, just to avoid confusion. So is this clear how we got this term?
Yes.
Okay. So this would imply this denominator is greater than equal to numerator as both of them are greater than 0. So, and you can take a square, and this is simply summation, or rather I'll write it as a1 square plus dot 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 plus an square, and b1 square plus dot 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 plus bn square is greater than equal to a1 b1 plus dot 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 an bn whole square. That's Cauchy-Schwarz. And again, for the equality quiz, it's a bit tricky over here. If you check, we should have, for equality, all of the AMGMs must be equal. So it would imply xi equal to yi for all I. But that would imply ai by bi is equal to the sum, rather, yeah, is the root of the sum of ai squares by the sum of, I'll again use a different index, j squares. This root. And this is independent of I. Hence, again, this is the constant quantity over here.
I or BJ?
Yeah, it's bj over here. The
Yes.
RHS is j. It doesn't matter actually. Actually, the reason I'm using j and I because these two are independent of each other. This is a constant that, as this does not vary with our some xi, it's basically not dependent on I. It's a sum of all the squares. That's why I don't want to sort of use the same I in two different places having two different meanings. One is varying and one is a fixed thing. So let's avoid that. That's why I'm using AI and BJ. J's are the fixed things and I is the variable over here. So that's why I've written for all I and stuff. Okay, so this is the proof of Cauchy-Schwarz, which I was saying using AMGM. Also, the funny thing is, like, we just saw that AMGM implies Cauchy-Schwarz, right? From our proof, implies Cauchy-Schwarz. Yeah, and very trivially, a square plus b square times b square plus a square, that's greater than equal to ab plus ab, right? Wait a second. And this would imply b square is greater than equal to 2ab, and which is AMGM. So, and from a previous proof, we saw that Cauchy-Schwarz inequality is equivalent to the square inequality to some extent. So all these inequality, Cauchy-Schwarz, AMGM, AMGM-HM, power mean, square, everything is based on the square inequality or the order properties of real. We are not actually doing anything new. We already have these properties. We are just reformulating all stuff so that it becomes a bit more beautiful and easier to handle and more robust, you might say. So I think that's it for today's class. Or, well, yeah, I think that would be it for today. In the worksheet, you might see some more problems. Let's do something. Instead of stopping right now, because you said that you guys tried the worksheet, let's see two hints, rather two problems from the first worksheet. You have seen the first worksheet, right? So before I end the class, let's revisit the first worksheet once. Panit, আর কতক্ষণ আছে রে এই ক্লাসটা?
6:35 অবধি, মানে 9 মিনিট আছে।
9 minutes আছে. Okay, I'll give you hints for them. I won't be able to solve it, but let's see. So tell any two problems which you want to discuss. I won't be discussing these problems. Wait a second. I won't be discussing 15, 11, 10, and 8.
Just
These
a
are
sec.
a bit.
Till the 14th one.
14th one. Okay. Yes. So 14th one is a good one. I hope you know this formula. 14th, 1 plus 2 plus 3 plus dot 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 plus n is equal to
Plus 1 by 2.
and by AMGM by n is greater than or equal to n factorial whole to the power 1 by n. That's AMGM. And this is equal to n plus 1 by 2. So that's one side of the inequality. This would imply n plus 1 by 2 whole to the power n is greater than or equal to n factorial. That's the first part. And for the second part, AMGM won't help. It's pretty obvious. So how should we proceed? Try to prove the following. It's a pretty simple thing. For I equal to 1 to n, show that n plus 1 minus I times I is greater than equal to n. This is based on your wavy curve method, which Sahil discussed most probably. And this, let me just help you out. This is equivalent to I. Oh, 1 second, sorry. I minus n times I minus 1 is lesser than or equal to 0. And can you use it to complete your proof? Well, it should help you.
Can you explain again?
Yeah.
I didn't understand from I equal to 1.
I equal to show this thing. Show if I is equal to one of these, 1 to n, anything of this, then n plus 1 minus I times I is greater than or equal to n. Or equivalently, to show this is equivalent to showing that I minus n times I minus 1 is less than equal to 0. And that's wavy curve, right? Wavy curve implies this thing. That should help you out. Did you get it, what I said now? I can be any variable in this way. Rather, I should write I belongs to this set. Then this is true. This inequality is true.
Meeting is going to end in 5 minutes.
Okay. 5 minutes, right? So maybe one more example. So tell another problem. I'll just state a hint for you. Anyone? Any doubt? Any problem? Feel free to share. Most of it wasn't.
Part 3.
Which one? Okay, so did you ask the last one? This one?
Yeah.
Okay, so let's give someone else a chance over there. I'll discuss more problems in the next day, and then Juanit and Sahil and the team would help you out also. But let's give someone else a chance. If no one else has a doubt, then I'll help you out. So anyone else? Do you have a problem over there which you want to ask or discuss? any problem out of these other than the ones I mentioned. So no one. Well then, you ask a question. I think no one has a doubt, or maybe which part 3? Which question? 6.
Part 3, we did a similar problem to this IMO SL1, but it's a bit different.
Problem 6, right? You're not audible. Which problem I did not get? I just heard part
6, part 3.
Problem 6, part 3. Okay then. Well, 6, part 3. AB by a to the power 5 plus b to the. This is a symmetric inequality, by the way. You were saying asymmetric that time. So this is a symmetric inequality. Plus BC by b to the power 5 plus c to the power 5 plus BC plus CA by this is less than equal to 1 if ABC equal to 1. All positive. Okay. So you can go about this one with different methods in other problems. Very helpful thing over here is something which is known as normalization. You can use it. That's making the denominator and numerator of the same degree.
Is this which question this is?
6, part 3. Can use the normalization process as well.
This exactly is done in 2 classes back of inequalities. So
You have done this question, so then I think you shouldn't have a problem in that case.
yes, just check the IMOSL 1996 question which was solved in the first basics inequality class.
Oh, okay then. Basically, it's the same question in that case, so you shouldn't have a problem. Yeah. So, okay. And any more questions? I think I still have. No, I am out of time. Sorry. One time session.
So next day 5 to 7. Saturday.
5 to. Let's see, 5 to 7. I'll let you know. 4 to 6 or 5 to 7. Okay.
Okay.
Do you guys have a problem with 4 to 6?
No, Dada.
Then 4 to 6 ही राखी পরের দিনে ওটাই বেটার হয় তো 4 to 6 টাও একটু এক্সটেন্ডেড হয়ে যায় তো সেই জন্যই বলছি ওকে দেন চলো best of luck, try the assignments. I'll discuss rearrangement inequality as well. I think you already know it from the first class, a bit of it, and then I'll discuss rearrangement